Hopefully you feel like that idea of marginal functions was pretty straightforward, just, subtracting two function values. The bad news is that even though that is the idea of marginal analysis, that's not how it's actually performed. And the way it's performed is going to feel probably less straightforward to you. But let's jump in. Marginal analysis in the real world. Even though all the business people will tell you that marginal analysis is just taking the difference in output when you change the input by one, in fact, the word marginal in practice is used to mean instantaneous rate of change. In other words, the marginal cost, which is often denoted with an MC, is defined to be C prime of X. And the marginal revenue, often denoted MR with capitals, is defined to be R prime of X. And the marginal profit function, MP, is defined to be P prime of X. For example, given those same functions we used before, let's find the functions marginal cost, marginal revenue, and marginal profit. And then we'll use those to revisit what's the marginal change when X equals 300. Okay, here we go. The marginal cost is defined to be C prime of X. That's the derivative, of course. So the derivative of 500 plus 2X is just 2. The marginal revenue is defined to be R prime of X. The derivative of 8X is just 8. And last, the marginal profit is defined to be P prime of X. The derivative of 6X minus 500 is 6. These are all constant functions, so it doesn't actually matter what the input is, but I'll go ahead and write this out anyway. The marginal cost at 300 units is C prime of 300. Well, C prime is always 2. That's $2. That's the same answer we got before. The marginal revenue at 300 is R prime at 300. Well, R prime is always 8, so that's $8. And the marginal profit at 300 is P prime of 300, which is $6. Let's see another example. Given C of X equals X squared plus 1, find the marginal cost function and evaluate the marginal cost when X equals 2. Marginal cost is defined to be the instantaneous rate of change of cost, in other words, the derivative of the cost. And in this example, that would be 2X. So the marginal cost when X is 2, C prime of 2 would be 4. Now let's compare what we just did to where we started this discussion. In other words, let's compare it to C of 3 minus C of 2. Notice these are C's, not C primes. This is mimicking what we did at the very beginning of the section where we said change in cost is the difference in two cost values. So let's see what happens if we use that idea. Let's see, C of 3 is 3 squared plus 1, and then we're subtracting C of 2, which is 2 squared plus 1. let's see, that looks like 10 minus 5. I'm not going to do anything fancy there. So we get 5. And now, notice these are not the same. So this using the derivative for the marginal stuff, it seems kind of bad. I mean, first of all, up here, where we used the derivative instead of simply subtracting the two function outputs, we got the same exact values. So what's the advantage to using the derivative? I mean, just subtracting two function values, two costs, is pretty straightforward. You don't have to understand any calculus to do that. But if you're going to use a derivative, then you have to understand calculus. So what's the improvement here? And now it's looking even worse because when we use the derivative, we did not get the same answer. What's going on here is that we're using the derivative as an approximation of the difference in the two function values. And in the next video, I'll explain why the derivative is an approximation and why we would want to use it instead of just subtracting the two function values.